started to introduce the idea of various functional groups and begin to discuss the structures of organic compounds, we're going to continue on that theme today, and we're going to take our way through some more functional groups, and then we'll wrap up on Friday looking at some more functional groups and perhaps reactivity. We talked about alcohols last time that contain the hydroxy functional group, and we talked about alkanes that don't really contain any functional groups. Let me talk briefly about alkenes and alkynes and aromatic compounds. So alkenes, like alkanes, are hydrocarbons, but they're hydrocarbons that contain carbon-carbon double bonds. Alkynes contain carbon-carbon triple bonds. And as we were talking about structure and bonding and thinking about some pi bonds and sigma bonds, we already got to see some simple alkenes and alkynes. We saw, for example, ethylene, CH2, double bonded to a CH2. We said the molecule is planar. It has a pi bond between the carbons. Ethylene technically is a trivial name for the molecule. Technically, although I don't think you'd hear anyone have it roll off their tongue, technically the IUPAC name, the systematic name for this molecule, is ethene. Often the very, very smallest compounds containing 1, 2, and sometimes 3 carbon atoms, the trivial names have taken over and just end up getting used almost completely. But then for bigger compounds, systematic names end up being the ones that are typically used. So for example, this molecule, CH2, double bond CH, and then another CH2, CH3. This molecule most people would refer to as 1-butene. And you'll get more on the systematic names of these compounds as we go into chapters that detail them. What you should be doing right now is just hearing the names and letting them wash over you and becoming familiar. So these are 2 alkenes, and then if you want an example of an alkyne, we've talked before about acetylene. A CH triple bonded to a CH. And again, the systematic name for this compound would be a little bit different. It would be ethine. And again, normally you wouldn't end up saying this. Well, alkanes are pretty inert. They don't react with much of anything. On the other hand, alkenes and alkynes are more reactive. For example, they react with bromine. going to learn more about the reactivity of these compounds as you go into the chapters that deal with them, but I'll just show you an example of one reaction right now. So let's take our 1-butene and see how it reacts with bromine. Bromine's a halogen, and the way you can tell that a reaction has occurred with bromine is very simple. Bromine is a red, dark red, blood red, fuming liquid that has these red-brown fumes over it. If you drip bromine, or a solution of bromine in an inert solvent like carbon tetrachloride, into an alkene, the color goes away instantly, and that's the chemical reaction. So immediately you can tell that 1-butene or another alkene has reacted with bromine because you get a colorless solution. And so, for example, 1-butene would react to form 1,2-dibromobutane. I'll write out the name, and again, don't sweat right now about the names. You're going to see these more later on. Now, by contrast, alkanes don't react with halogens. They don't react with much of anything except under special conditions. So if I simply mix ethane, which is a gas, with bromine or bromine vapors, you don't get a reaction under ordinary conditions, but there's a big caveat. And that is, if you have an energy source, if you have light that has some UV in it, or even some violet light, or you have a good heat source, you heat the reaction mixture up, then you get reaction to give bromoethane. And so the big difference is if I take an alkene and I drip in bromine or a solution of bromine and carbon tet that's bright red, the color goes away right away. If I take an alkane like hexane and I add bromine, you see no change in the color. All right, another class of hydrocarbons, unsaturated hydrocarbons, are aromatic compounds. You'll learn more about aromaticity later on in the, I think in the B course or possibly the C course. But generally, not always, aromatic hydrocarbons contain benzene rings. Let me give you a few examples of aromatic hydrocarbons. Benzene itself, of course, contains benzene rings. It's an aromatic hydrocarbon, simplest. Naphthalene, anyone know where you might encounter naphthalene? Mothballs, excellent. So naphthalene is a solid. It's crystalline. It's actually very beautiful, big flaky crystals. And okay, you're in the lab course right now. Have you done a crystallization experiment yet?
Yeah.
Yes. When you see crystals coming out, to me that's magic. I mean, this is beautiful. These little snowflakes coming out. Well, naphthalene has some of the most beautiful crystals you can see. Benzene is a liquid. It boils at 80 degrees. It used to be widely used as a solvent to dissolve things, but they found it was a little bit carcinogenic, not super carcinogenic, but mildly carcinogenic. And so slopping it all over as a solvent generally is verboten, and it's only used very carefully now. I'll give you one more example so you see the diversity of things that we would call aromatic compounds. This compound is called phenol ethane. And when you have a benzene as part of a molecule, you say that the benzene is a phenyl group. When I write out problems for the course, for quizzes, midterms, problem sets, I often like to take examples from real scientific literature where people have really done experiments. And often the molecules will have a phenyl group in them. So you may see a phenyl group as a common feature of an organic molecule. Generally, aromatic compounds are less reactive than alkenes and alkynes. So for example, if I take benzene and I add bromine to it and just mix them, there's no reaction. But if you want to make them react, which chemists often do, you can add a catalyst. So for example, if you add a Lewis acid catalyst, I'll again put this as a big except. An example of a Lewis acid catalyst that one might deliberately add to make this reaction occur would be, say, iron 3 bromide, ferric bromide, FeBr3. So I'm giving you a little bit of a flavor of different chemistries right now. And so this is a reaction that you'll see later on. But aromatic compounds in general, if you were to think about how to test for whether something were an aromatic were an alkene or an aromatic compound, adding bromine would be a good test. Now, later on you're going to learn that there's a special stability to the benzene ring, that there are over 30 kilocalories per mole extra stability, about 36 kilocalories per mole, associated with a special property called aromaticity when you have 3 double bonds in a ring next to each other. But that's just a little taste of what the future has to hold in terms of your learning. when we were at the end of last class, we were talking about alcohols. And we said that alcohols like ethanol, methanol, small alcohols are miscible with water. They mix in all proportions. Bigger alcohols like 1-butanol dissolve in water, but they're not miscible with water. And very big alcohols don't dissolve in water to any appreciable extent. All of the molecules that I've just shown you, all the alkanes, the alkenes, the alkynes, are hydrophobic. They don't dissolve in water at all. Benzene doesn't mix with water. Naphthalene crystals float on top of water. 1-butene doesn't dissolve in water to any appreciable extent, and neither does ethane. And the big difference is polarity. Like dissolves like. Water has hydroxyl groups, water is polar, so water dissolves molecules with polar functional groups if there isn't too much grease. A good rule of thumb on solubility, and it's very hard to come up with absolute rules here, so this is what I would call a rough rule of thumb. Is if a molecule has, let's say, one nitrogen or oxygen containing functional group for 5 or fewer carbons, it will be soluble in water. Hesitant to write this up on the blackboard because there are plenty of exceptions to this rule, but it's a very good starting point for thinking about what's going to be soluble in water. And this is important because in your laboratory course, you're going to be dissolving compounds in water and organic solvents and trying to get them to go where you want them. And you're going to be wondering what's soluble in what. This is also important in medicine. This is super important in medicines because companies spend $1 billion to develop a new medicine that's going to cure disease. And if the medicine doesn't have the right solubility properties in water, it's not going to get into your bloodstream. It's not going to get where it's needed. It's going to pass right out of your body through your digestive tract, and it's going to be a dud. So these properties of water solubility and another property called hydrophobicity, which talks about how the molecule will partition between greasy solvents and greasy tissues in your body, these are very, very important properties in medicine. All right, another generalization that I'll make, and again I can come up with exceptions and maybe later on I'll mention one or two, is that most organic compounds are soluble in other organic compounds. More specifically, inorganic solvents. the laboratory, it's very rare that you would mix two chemicals directly without a solvent to dissolve them. A solvent helps bring them together. The solvent helps dissipate heat when they react, because many reactions are exothermic, and if you just mix two pure chemicals, they may react very violently. And a solvent helps you direct the compound where you want, for example, to put it into a solvent layer, an organic layer, and to wash away inorganic chemicals, something that you're going to be doing a lot in the laboratory course, wash away inorganic reagents that you add to the reaction mixture. So some typical solvents are things like diethyl ether, CH3, CH2O, CH2, CH3. When I talked before about freebasing, generating the free base of amines or amine drugs, one thing that's often done is to use diethyl ether as a solvent to isolate the free base. And in the case of some drug users, as in Richard Pryor, I believe, it resulted in a very bad burn when he used combined flames and the organic solvent diethyl ether. Another organic solvent is hexane, CH3, CH2, CH2, CH2. Hexane is an alkane containing 6, hence the hex carbons, 1, 2, 3, 4, 5, and CH3 makes 6. Another example of an organic solvent is dichloromethane, CH2Cl2. And precisely for reasons of hazard like flammability, in industrial processes where they isolate large quantities of organic compounds, non-flammable solvents like dichloromethane are often preferred to flammable solvents because of the hazard that's posed when working with a large amount of a flammable liquid. All right, what I'd like to do now is to start to take a traipse through various other functional groups. Most of the functional groups contain what organic chemists often refer to as heteroatoms. Heteroatoms are just a shorthand for atoms other than carbon and hydrogen. So we already talked about alcohols, compounds with the structure ROH that contain the hydroxy functional group. Closely related in some ways to alcohols are ethers. The general structure of an ether is ROR, or I'll say ROR prime. R prime just means it can be a different R group, a different alkyl group, or it can be the same alkyl group. We call the OR group an alkoxy group. So for example, in diethyl ether, I drew it on the previous board, but I'll draw it again over here, CH3, CH2, O, CH2, CH3. We can call the OCH2, CH3 an ethoxy group. ETHOXY is ethoxy. So, alcohols, of course, are like water, I mentioned before, where you have one of the hydrogens replaced by an oxygen. Ethers are like alcohols, where now you have the second H replaced by an alkyl group. Did I say hydrogen? Where you have one of the hydrogens replaced by an alkyl group. There are lots and lots and lots of relationships, and this is what to me makes so much sense about organic chemistry, is when you start to look at molecules as part of families, and then families being interrelated in various ways, you realize these are not just a disparate collection of facts, but rather relationships that fit into a bigger picture and are uneasy to understand as part of a bigger picture. So if you move down the periodic table from oxygen down one row to sulfur, then you just come up with the sulfur analog of an alcohol. And the sulfur analog of an alcohol is a thiol. The general structure of a thiol is RSH. We call the SH a mercapto group. And I'll give you one example of a thiol. CH3, CH2, 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 OH, SH. My mind is still one row up the periodic table. So this molecule is called 1-butane thiol. Sometimes you'll also hear it referred to as a common name of butyl mercaptan. This molecule stinks. Most thiols smell really, really bad. The receptors in your nose are designed to pick up polarizable polar atoms, and you end up smelling them really well. They're metals that bind very strongly. You've smelled butyl mercaptan before. Anyone know where you've smelled it? It's used somewhere. In gas, in natural gas. Methane doesn't actually have any odor to it. But you don't want to have natural gas not having an odor to it, because if you have a gas leak in your stove or your water heater or your furnace or in one of the gas pipes in your house will fill up with an odorless gas until it ends up blowing up when some spark source sets it off. So they add just a teeny bit, parts per trillion or parts per billion, a minuscule amount of butyl mercaptan to warn you. And the risk of a natural gas explosion is very real. There was an article in the New York Times last year, I believe, about somebody who was involved in a bitter divorce in New York City, who opened the gas in his house to fill it with gas, and this multi-million-dollar townhome in New York blew up from the mixture of methane and oxygen and whatever fire source was in the house. And of course, if we talk about use of things, one of the biggest uses of alkanes is as fuels. They're present in gasoline, there's natural gas, they come from petroleum, as do alkenes, alkynes, and aromatic compounds. They are all present in petroleum, which is the starting feedstock for many, many organic compounds. All right, nitrogen and oxygen are the biggies for most organic containing functional groups. There are many, many functional groups that end up containing nitrogen and oxygen. Amines are the simplest nitrogen containing compounds. Just as alcohols and ethers are related to water, amines are related to ammonia. And so, for example, I can write RNH2, that's an amine. R2NH, that's an amine, just as we have an alcohol with one group on water, one group on oxygen, and ether with two. We can put one, we can put two on nitrogen, just like you would replace the hydrogens of water with the alkyl group. You could replace the hydrogens of ammonia with an alkyl group. And of course, these could be two different ones. It could be R, NH, R prime. And you could put three groups, R3, N, or three different groups. I'm not going to write them out. Just like we make little distinctions, or we make distinctions among alcohols and ethers, and they have some different properties. We make distinctions among amines. We call an amine with one R group a primary amine. An amine with two R groups a secondary amine. And an amine with three R groups, the tertiary amine. In an amine, we refer to the NH2 group as an amino group. Technically, there's a different name, for example, for the NH in the secondary amine, but I think most people would just refer to it as an amino group. Technically, it's called an imino group, at least in some circles, but I wouldn't worry you with that distinction. And I'll just give you a couple of amines. Again, you will see nomenclature later. CH3, NH2 is called methylamine. It's a primary amine. An amine with three ethyl groups on the nitrogen, CH3, CH2, 3, N, meaning that all 3 hydrogens of ammonia have been replaced with ethyl groups, is called triethylamine. So we've already talked about amines as being present in amino acids, I think I mentioned earlier in the class when we talked about polypeptides and proteins. Amines are present in many natural products. There's a whole family of natural products called alkaloids, plant compounds that contain amines. Many of them have biological activity. I mentioned one of them when I talked about cocaine and making the free base of cocaine. Let me draw up another amine, another alkaloid that's also very biologically active and very important in medicine. Let me draw the structure of morphine. And I want to do this for 2 reasons. One is I'd like you to see how the pieces that we've just talked about fit into a real organic molecule, a big biologically active molecule. The other thing I'd like you to do is to see how you can draw these structures yourself. So we're going to draw the structure. I'm going to draw it very slowly, and then we're going to identify all of the functional groups in this very important natural product. Morphine is used widely as a pain reliever. It's an addictive pain reliever. It's often the pain reliever to use after surgery or when people have very painful cancer. It is a chemical precursor to heroin, which is made synthetically. So I'm starting my drawing of morphine by drawing a benzene ring. And I'm going to draw it horizontally just to make it a little bit easier to draw. I'm going to connect this benzene ring to another 6-membered ring. This 6-membered ring is not a benzene ring. There's one double bond in this 6-membered ring. There's also an oxygen atom connecting the 2 6-membered rings. And I'm going to draw a wedged line here, a hashed line here rather. Remember we used hashed lines to mean going back into the plane? There's what we call stereochemistry at that carbon. You're going to learn more about this later, but we've already seen the concept of representing 3 dimensions in 2 dimensions by using dashed and hashed and wedged lines to represent respectively going back into the plane and coming out of the plane. I'll draw one more 6-membered ring up on top. And there's one more ring in this molecule. I'm going to draw a wedged line, a bold line, to represent that the stereochemistry of this carbon has the next carbon coming out of the plane. And then I'll draw another line here. If you're very good at drawing, you can help show the 3-dimensional structure by erasing just on the edge of this line to show that this other line has come over. Most people these days probably wouldn't do that by hand. It takes a little bit of planning, but if you're a better artist than I am, then you might do that. I'm putting in a nitrogen in the molecule, and I'm connecting that nitrogen up to this carbon. There's also a methyl group on the nitrogen. We have a hydroxy group on this ring. A hydroxy group on the other 6-membered ring on the right. And I'll show one more piece of stereochemistry. Hydrogen coming out of the plane. All right, well, this molecule that wouldn't have made sense to you at the start of the course now has some meaning, and we can see some pieces to it. What's that piece? The benzene ring, an aromatic ring. This piece, hydroxy group. Same over here. What would we say this oxygen is part of? It's a heteroatom, and what would we say the functional group of an oxygen with 2 carbon substituences on it? It's an alkoxy group, and we would call that group an ether. So the distinction is, we would say that the OCH2CH3 in diethyl ether is an alkoxy group, is an ethoxy group. The oxygen itself is an ether oxygen. Over here, double bond, so we have an alkene group. Hey, what does this mean about morphine? If I added bromine to it, it would react and the color of the bromine would disappear. We would go from red to colorless. What type of amino group do we have up here? Tertiary amino group. So there we've seen alcohols, amines, aromatics, ethers, alkoxy groups, or amino groups, all in one molecule. All right, let's continue with our discussion of heteroatoms, and we'll take a look at alkyl halides. Alkyl halides, of course, are compounds containing a halogen. So, for example, CH3Br we would call bromomethane. It's another name for this molecule methyl bromide. Where have you heard of methyl bromide before? Half an hour ago. Anywhere else? Newspaper, news sources? Methyl bromide used to be used up until a few years ago as a fumigant on fields, on crop fields, like for strawberry crops, because it's poisonous and it kills various pests in the ground that attack the strawberry plants. It's also destructive to the ozone layer, and so now its use, I believe, has been banned in agriculture, and that's probably a good thing. Of course, they still pump toxic stuff into the ground to kill pests. They just pump different toxic stuff into the ground. So we would call the Br in methyl bromide and bromomethane a bromo group. We move along the periodic table. CH3Cl would be chloromethane. This is a chloro group. Chloroalkanes used to be widely used. You've heard the term CFCs. These are chloroalkanes that contain a chlorine group and a fluorine group. And Professor Sherry Rowland here at UCI discovered that hydrocarbons, chlorofluoroalkanes, destroy the ozone layer. And so eventually, after many protests from companies like DuPont and lots of resistance, they were banned. And now, in your air conditioning, instead of chlorofluorocarbons, you find HFCs that have some hydrogen in there, hydrofluorocarbons, that end up not being as destructive to the atmosphere. So if we move up in the periodic table, CH3F would be a fluoroalkane, it would be fluoromethane. And eventually, Sherry Rowland was recognized for this with the Nobel Prize. And finally, let's just move back down, CH3I, iodomethane, respectively containing fluoro and iodo groups. All right, well, I think this is a good time to stop our discussion of heteroatom-containing compounds. Next time, we're going to pick up talking about carbonyl-containing compounds. We'll discuss ketones, aldehydes, esters, amides, carboxylic acid, and then we'll move on to some properties of these